I'm going to talk pretty quick on this because this is really just a discussion of computed radiography, not really the techniques of it, although towards the end we'll talk a little bit about how this impacts techniques. In general, the big takeaway from this lecture is that given the way this technology works, computed radiography should have a lower patient dose, a lower technique than film screen radiography. And that's largely because we can turn up the KVP and turn down the mass and get the same basic image. One thing to look at before we get into the lecture proper is on page 283 in our textbook. There's a whole bunch of abbreviations in the chapter related to computed radiography. The really important ones are PSL, which means photostimulable luminescence. PSP, it does not mean PlayStation. It means photostimulable phosphor. It's a very thin plate of photostimulable phosphor inside of the CR image receptor. Another one is SPS. It's the storage phosphor screen. So inside of this thing there's a screen that stores the phosphors. And a significant thing about this SPS is it's the part that we really can see. It appears white. So when we open up a CR image receptor plate, we see this white screen. So it reflects, that's because it scatters light off of it. And that property of scattering light we're going to call turbid or turbidity. It means that there's a limit within the screen in that as it's sensing the X-rays, it's simultaneously scattering light. So we have to figure out ways to account for that. So let's look at a photostimulable phosphor and a PSP in like kind of cutaway. So if we were to remove a PSP from the image receptor, we would have we would largely be touching a protective coating. You can see there's a protective overcoat. So the furthest, kind of the most superficial element of it is a protective coat. And then within that, and you'll notice it's about 100 to 250 micrometers in thickness. And it is largely a phosphor with some kind of binding agent. And these crystals inside of the phosphor are kind of like the sensitivity specs inside of the film. So they're kind of all throughout this phosphor plate, and they're very small, like 3 to 10 micrometers in measurement. So an individual crystal might be 3 to 10 micrometers. A lot of times they're made out of barium fluorohalide with europium. So that's written BA fluorohalide BR with europium. And that europium is actually the sensitivity center of the crystal. Okay? And that's largely because it's what we call metastable, which means that when X-ray photon, so let's say we had a barium fluorohalide molecule here. If we have a photon that's incident on it, it's going to eject an electron, but that electron's going to remain in a metastable state. The atom's not, it's been ionized, but it's not super volatile. It's not bouncing around making free radicals and stuff like that. Then when we hit it with a laser, the electron, though, is going to go back inside of the atom. The electron will go back inside of the atom, and when it does that, it's going to emit visible light. And that's basically how the system works. The principal source of image noise with any system is scatter radiation. The principal source of noise is from the patient in the form of scatter radiation. But as you can imagine, with any kind of technological system, there can be noise that results from the system itself. And that's what this slide kind of indicates. This is found on page 292 in our textbook. So there can be mechanical defects, like the driver is moving too slowly, it's moving too quickly. There can be optical defects that result from the laser. There can actually be scatter of visible light that's produced by the PSP. So this laser moves over the area, the light is produced, and it scatters in a way such that spatial resolution is lost. And so that's this light quanta and scatter of stimulating beam. And then there can be computer defects. There can be noise related to the computer. It can be inadequately sampled. It could have some kind of frequency problem, or it's not quantitated correctly. Even something like a solar flare, right, could influence the system. Okay. A significant thing about the PSL, this photosimulable luminescence system, is that it operates very similar to the OSL that you wear to detect radiation. So inside of this badge that Landauer produces is an optically stimulated luminescent crystal. It's actually the exact same stuff that's inside of PSP. So the exact same stuff that we are using to capture the remnant beam exiting the patient is the same stuff that's inside of this crystal made by Landauer that we use to detect our occupational exposure. And they go through a very similar process of stimulation with a laser and then readout. Light is emitted when an optically stimulated luminescent crystal is stimulated. The same thing happens with a PSP. So when an X-ray beam exposes, and this here we see the X-ray beam exposing the PSP in this image right here, the energy transfer results in an excitation of the electrons that are there. Okay? And so they wind up in what we call this metastable state, where they're not really bothering anyone, no one's bothering them, the atoms are just kind of resting. Now, approximately 50% of those electrons are going to immediately jump back into a nearby atom. 50%. And so they're going to emit light right off the bat. You're going to shoot it with the X-ray, and inside the CR image receptor, there's light that's going to be given off, a very small amount of light that's going to be given off by the PSP as we expose it to X-rays. Okay? So the significant thing here is that these electrons even though they're metastable, they want to return to a grounded state. So if we do not immediately develop a CR image receptor after exposure to X-rays, we will lose our image. The textbook says in about 8 hours, the image will fade to where it's no longer registerable by the reader. So when we're out on portable work, we're shooting X-rays, we decide to go to lunch, and lunch became, National Tequila Day or whatever, and we forgot to, and that was all the X-ray tech students talked about yesterday was
National Margarita.
Yeah, so whatever. We come back 4 hours later, develop our image. Chances are it's not going to be as good of an image as it would have been initially when we first took it, okay? Because we lose some of it, it fades. In roughly about 8 hours, it's completely lost. Okay, this next part is what occurs inside of the reader. So the first part was what happens as we're taking the x-ray. This part is what happens when we insert the CR cassette into the reader. It scans over it with an infrared laser light. Okay, a lot of times they're a helium nitrogen gas laser. So it's red in color, which means it has a longer wavelength, but it has a very small diameter, about 50 to 100 micrometers. So again, very, very small, basically roughly the width of the actual photostimulable phosphor plate. Okay. As we increase the strength of the laser, we will simultaneously increase the strength of the light emitted by the PSP, by the crystals. As we increase the laser strength, we will increase the light emitted by the laser. And interestingly enough, the diameter of the laser has a direct effect on the spatial resolution of the resulting image. So we want a small, very, very, very small diameter laser that's going to scan over this. That's why it takes some time to develop a CR image. It's limited by the size of that laser as it's scanning over the huge surface of the image receptor plate. Okay? When it scans over, the photostimulable phosphors with the laser, they're going to emit light. So the metastable electrons will return to the atoms, and in that process they will emit light. Now the light is going to be in like the blue, green, indigo spectrum, right? So let's talk a little bit about that. In terms of wavelength, right? When we're talking about the electromagnetic spectrum, let's say. Over here in the small wavelength, we have things like gamma rays, right? Then X-ray, small wavelength, ultraviolet, yep. And then right in here, we have a little break, a little tiny break where we have visible light. And then as we get bigger and bigger wavelengths, we have things like infrared. And I mentioned the laser is infrared. Oh my goodness, I cannot write. Radar, like FM, then like TV and things like that. In this region here of visible light, which is what's occurring inside of a CR reader, over here we have the red, so bigger wavelength, and over here we have the blue. And this is important because the laser has what we call a discrete wavelength. It does not vary. It's not a spectrum. It is just a laser, period. It's red. It's the color of red that it will always be when you give it a certain amount of electricity, period. So it's what we call discrete. It has a peak to it, right? And it's a very narrow peak. The blue side of things is a spectrum. So as the laser scans over the PSP, it's going to emit a spectrum of blue light. And that spectrum is going to be more like a spectrum of energies. So it could be any level of these different blues. Now the significant thing from the standpoint of the reader is it's reading this light emission from the PSP into what we call a, analog to digital converter, an ADC. And this is essentially the same thing as what's going on inside of a CT DAS, the data acquisition system. It's the same thing. I have a digital analog signal of light. I'm digitizing it, period. Right? Now, I would want to digitize a certain spectrum of energy, right? Basically, any blue-green kind of light, indigo lights, I'll want to digitize. I do not want to digitize anything that's red because that's the laser, right? I don't want to digitize the laser. Just want to digitize certain wavelengths. So the computer has a way of knowing what wavelength, what color the light is. This is how the latent image in the PSP is made visible. So as this analog to digital converter works, it is going to be digitizing the image, and eventually, after it applies its histogram analysis, it produces the X-ray image. It does not have to go through all the weird filtered back projection stuff that a CT scanner does. It just renders it in relation to where it was at in the PSP. So it's a one-to-one relationship in terms of the geometry from the computer standpoint. Nevertheless, we can lose signal to scatter of light. So I mentioned that the plate itself is turbid. It scatters light in the form of white light. And then we can also have some signal loss to the photodiode of this light, this camera here. It's what we call a photodiode. It's the exact same thing that we were using when, do y'all remember the lab team that made the photometer and measured inverse square law? Inside of the electronic learning lab, there's a photodiode that receives light energy. That's all this thing is. Now we're going to need to erase this stuff, and so the way that we do that is we flood the PSP with an intense white light, typically from fluorescent light bulbs. It looks like, this is the part of the scanner, the reading function where we actually see it looks like it's making a Xerox, right? It's wiping out any unread, unexposed molecules of the barium fluorohalide with europium. And it's best to use the image plates soon after erasing them because they are sensitive to natural background radiation. They can be fogged by radiation. So you all know that whenever we go into the lab, I ask you to go ahead and erase the CR cassette before you do an experiment because it's maybe fogged. We haven't used it since last week. It hasn't been erased since last week. So it might have some fog in it, and that could significantly impact our images. So as a rule of thumb, if I don't know whether or not something has been read or erased recently, it's probably best just to go ahead and erase it before I go and do a diagnostic exam with it. Okay. Let me see. One thing worth looking at, again, just in terms of these different kind of emission spectrums, is if you look at page 288 in your textbook, you have an illustration of how the solid state laser or the gas lasers are discrete colors. They are specific colors, red or orangish, but the emission of light from the PSP is a spectrum of light energies, anything from green to kind of purplish. One more thing, because it would be wrong for us to talk about all this stuff and not talk about image characteristics. So if we look on page, I think it's page 290 in our textbook, we're going to see some of the problems, and I think our lab team will be talking about this some today. Here we have on 291, you actually see an experiment similar to the experiment I showed you last week, where I used a film system and I made a series of exposures and changed the KVP, and you could see, or actually here they're changing the mass, you can see how it goes from underexposed in a film system to kind of burn out on the right hand side. But if I go down to the digital system, I have some quantum model on the left hand side, but otherwise the images look identical. And the final image is shot at 80 mass. Looks fine, right? He talks about, and this isn't the term that I would use to talk about this, but he talks about how the sampling frequency of these digital plates, I can't remember the term he uses for it. It's kind of a goofy term, just a sec. 4 decades. He talks about how they have 4 decades of receptibility. So let me talk about that real quick. So let's draw this out as it relates to optical density and exposure. Now, with a film system, what we have is what we call a characteristic curve. So with film, as we start to make an exposure, we see it goes up and then it plateaus out at some point, right? If we're dealing with a CR system, what happens is it's just a linear relationship, and it will continue to go. This is what he means by generations. It will continue to go up through 4 relative generations of sensitivity. So we could take this up as high as a radiation therapy treatment machine, and if it is not out of that generation of sensitivity, it will still be reading an x-ray of your hand. Right? In fact, this is what we do in radiation therapy. We take x-rays with the radiation therapy machine using this very principle. Because it continues to receive information. Okay? So in terms of image characteristics, we are still concerned with the 4 principal things, but they are going to change, unfortunately. And that's the bad news. The 4 principal things are spatial resolution, contrast resolution, noise, and artifacts. But all of them are going to be different for a computed radiography system versus a film system. So the principal source of noise is still scatter. But as I mentioned, and he mentions in our textbook on page 292, you should emphasize that the conventional approaches like KVP controls contrast and mass controls optical density just simply don't hold for CR system. Because CR image contrast is constant regardless of radiation exposure. So the images, the good news here is the images can be made at a higher KVP and a lower mass, resulting in an additional reduction in patient radiation dose. So if we apply these principles correctly, we can get the same picture at a reduced patient dose. But largely what happens is stuff more in this realm, where the stuff is not being applied correctly. We're overexposing the patient when we don't need to, because we know that when we overexpose the patient, we'll get a guaranteed picture and not have to repeat it. Okay?